Let's turn our focus now to standardizing data. First of all, we have this formula up here. We're looking for a z-score, which we're going to refer to as a standardized score. To find our z-score, all we're going to do is take our x value, our data point, subtract our x bar value, our mean, and divide that by the standard deviation from the sample. Let's say we're focusing on a data set in which the x bar value, the mean of the sample, is 20, and the s value, the standard deviation of the sample, is 4. What if we're focusing on the number 17? Well, if we wanted to standardize that data, all we simply have to do is take the 17, subtract the x bar value 20, and divide by 4. When I do that, I'm going to end up with negative 0.75. If I have a value of 26, I follow the same logic, and I can standardize that score. In this case, I have a z-score, a standard score of positive 1.5. What these two numbers tell us is the number of deviations away from the mean that data point falls. Obviously, a negative z-score would indicate something that is below the mean, for example 17, and a positive z-score would represent a data that is above the mean, for example 26. If your x value and your x bar value are the exact same, you'll get a z-score of 0, which means it's not any different than the mean. In a little bit, we'll talk about how we can use these numbers to take data sets that are not on the same level and compare them to one another. Say, for example, now we have two data sets, and they're scored on different levels. So you take a test that has an average score of a 500 with a standard deviation of a 100, for example the SATs, and then you take another test, but this test has a mean value of 40 and a standard deviation of 3. And we know in both cases I can't compare the scores that I earned, the 620 and the 44, I can't compare them because they're on different levels. If I standardize those scores, if I take the 620, subtract 500, divide by 100, I've now standardized this score as a positive 1.2. If I do the same thing to my other test, I end up with the standard score, a z-score of positive 1.33. These are now on even playing fields. So the fact that my positive 1.33 is a larger number tells me I did better on that test than the other. Let's turn to percentiles now. When we talk about percentiles, what we're talking about is the percentage of people that fall below you. So if you're in the 85th percentile, for example, and think back to when you took tests back in 2nd and 3rd grade and they said you were in the 85th percentile in reading, what it meant is that you scored better than or above 85% of the population. So when we talk about percentiles, if we're talking about the median of a set, that would be the 50th percentile. Anything above the 50th percentile would mean that you scored or did or are taller than the halfway point. Anything below the 50th percentile would mean that you were shorter or did worse or things along those lines. For example, if they say an infant's weight is in the 20th percentile, that means he or she is only weighs more than 20% of babies that same age. This formula over here is if we're given our data set. To figure out what percentile you're in, B indicates the number of people that scored below the score we're looking at. E is the number of people or scores that are even. and n is your total number of scores. So for example, if 500 people take a test, that would be my n value. If I scored better than 300 of those people, and I scored the exact same as 20, all I would do is plug into my formula and realize that this puts me at 0.62. So I'm in the 62nd percentile, meaning I did better than 62% of the population. We just focused on percentiles, and that was the idea of percent out of 100. Now we're going to focus on quartiles. And what quartiles are going to do is break our data set into quarters. They're going to break it into 4 chunks of 25% each. Well, think about what median meant. If I had the median of a list, I knew that it basically took my list and cut it in half. 50% to the left and 50% to the right. Well, if I take this lower half and I cut it in half, that's going to give me 25% and 25%. If I do the same thing to the upper half, I've now broken my data set into quarters. This point right here is referred to as my first or my lower quartile. This is referred to as my third or upper quartile. All quartiles do, along with the median, is break my data set into sets of 4. This is going to mean a lot more in our next section when we talk about a 5-number summary. We're going to use these two numbers, my lower and my upper quartile, and it's going to start to give us a little bit more meat to the word outlier. And what we're going to do with this right now is we're going to look at the word inner quartile range. And if you think about what the range was just simply the maximum minus the minimum. Your inner quartile range is going to be your third quartile or your upper quartile, and you're going to subtract your lower or your first quartile. And that's going to give you your inner quartile range. It's basically going to give you the range from your lower to your upper. We're going to tie this idea into the idea of how do we determine if a number is an outlier. We're going to use this inner quartile range. We're also going to use this when we talk about box plots and modified box plots.